Thank you so much. So I had to think about what to present at this occasion, and it seemed like it's kind of a big picture occasion. And I know I was told that Beau Honoré did this last year, and indeed I was sent a picture of Beau Honoré doing it last year, and I have modeled my costume on his, and because I think it's good to follow him in all things. And I thought, well, should I give an individual paper, which is what he did, so I didn't follow him in this thing, or should I give kind of a big picture sort of talk? And I decided to do the latter. And the idea was mainly because it was that kind of occasion, because I'm about to turn 60, and so I have been reflecting on time passing, both personally and intellectually. And I thought this would be a chance to codify some of those thoughts on a couple dimensions. So that's what I'm going to do. We'll see if you like it or not. I hope at the least to say enough provocative things that there will be stuff to talk about at the reception afterwards. So what I'm going to do, this is going to be a little bit like a book of short stories that are all interconnected in a way. I'm going to talk first about a bunch of things related to conditional independence. So much of my career, especially early on, I was known as like the matching dude. And, you know, that was a time, it was a very exciting time. It was a very close parallel to what we're going through now with machine learning. People were excited. It was going to be transformational. It was going to solve all their problems, blah, 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 blah. Everybody had their own matching estimator, just like everybody has their own version of the lasso or their own version of the random forest now. So I'm going to talk a little bit about that and my own and the literature's experiences as we sort of went through as a profession to learn about how to think about conditional independence as an assumption, and more importantly, or in more detail, about estimators that build on conditional independence, such as matching and weighting estimators. So that'll be the first part. There's some chance that that will consume the entire 45 minutes. I always have a dread fear of not having enough slides, so as a result, I always have too many. But if there is time left, I also want to do some reflections on model selection. And those of you who hear my talk at the Nordic Econometric conference this weekend will learn more about my recent reflections on model selection and things. But I wanted to say a bit about it here, because I think it's, in contrast to matching, it's something that, for me at least, has always kind of been there in the background. And having just moved from Michigan and Maryland, which were both very design-based places, to Wisconsin, which is a very structural place, and it has led me, in part, to be frustrated with the way that structural people think about model selection, but that has led me to think about model selection more generally. So I will say words about that, and then there's a slide at the end that lists all the things I thought about talking about, but realized there was no hope I was ever going to get more than 2 topics in. So first of all, and this slide comes from teaching undergraduate econometrics for a long time, but it also kind of illustrates how slow it is for me sometimes to notice things. And I think a lesson as I've been reflecting on these 2 subjects over the past few days has been that the profession is often very slow to learn things, the profession taken as kind of a whole. And I was slow to figure this out. So I've been teaching undergraduate econometrics since I was at Maryland, so since the early 2000s, and I've always used the Wooldridge book. I mean, it used to be the case, maybe it still is, that the first line of the Wooldridge undergraduate econometrics textbook was, suppose you're evaluating a training program, right? That seemed like the book for me. And so I used that book, but somehow along the way at Michigan, right after about 10 years, and after becoming more involved, I guess, in actually doing randomized trials and thinking about randomized trials and noticing that the textbook had nothing really about randomized control trials in it, which is odd. Because if you're like an Anchor style person, you kind of lead off by talking about randomized controlled trials. And then everything kind of flows from there as a sort of how do we get back to something that looks like a randomized controlled trial when we didn't do one. But there's nothing in Wooldridge's book, which is a very nice book. I love teaching out of it, about randomized controlled trials. Not only that, and sort of consistent with that, there's nothing in the book about the conditional independence assumption. And again, it took me like a decade to notice, oh, the entire textbook, I think I have a pointer here. No, I don't really have a pointer, so I'm going to jump up there. is about exogeneity, right? So if we write down a linear model, y equals x beta plus gamma d plus u, where d is the variable whose coefficient we care about, maybe it's a treatment, a program, something like that, right? We assume e of u given x and d is equal to 0. That's exogeneity. That implies a causal interpretation for every single coefficient. Okay, that's fine. But that's a lot stronger than you need if you only care about the coefficient on the d, on the treatment indicator, right? You don't really care. In fact, you may be quite sure that a lot of those other variables did not have causal coefficients, right? If you're evaluating an active labor market program and you have put lagged outcomes in there, you don't want to interpret those coefficients causally, but you want the variables to be in there because you think they're helping you make the conditional independence assumption more true, right? So the conditional independence assumption in Stock and Watson, which is the other leading undergraduate econometrics textbook, it gets a footnote. That's it, one footnote. Oh, by the way, some people talk about this conditional independence assumption, which says that conditional on x, I can have a causal interpretation of the coefficient just on d. Well, does any paper ever actually assume exogeneity? Right? This is a whole book. Both these whole books are about exogeneity, which no applied person that I know of in any recent paper would ever actually assume. Why do we teach it this way? That's strange. Now, maybe this is a kind of technological story, but I don't know what the story is, but it seems like an interesting question, right? So both these books are like 30 years old. 40 or maybe 30 years old, right? And they, there's a whole thing that you do when you write a textbook that is successful, which is you revise it every 3 years so that you make the previous editions obsolescent or obsolete, and then you get more sales and blah, 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 right? So these books have both been revised 6, 7, 8, 9 times. And they do, they move a little bit, but it's very hard when you write a book, I think, to go in and wholesale toss out a chapter and write a chapter again. You're busy. You're writing papers. And so I think we get in this situation where the books reflect what was going on a long time ago, even as they are updated, and not what we're doing now, or maybe what we ever did. I don't know. So this is puzzling. This is my first remark about conditional independence. Why don't we teach it to the undergrads? Seems like we should. So over time, my undergraduate econometrics course evolved to say more about conditional independence and randomized controlled trials from its base in the Wooldridge book. All right, that was sort of in parametric model land, although conditional independence also applies to matching. Let me talk a bit about the early days of matching. So it was all very exciting being at graduate school in Chicago, and these papers by Deheja and Waba show up, right? So they're graduate students at Harvard. They're working with Don Rubin in the statistics department, even though they're econ grad students. Waba's going to leave and go to Wall Street and never reappear. So it's all about Deheja, in fact. And if you look at the early drafts, and I kept some of them because I imagined that someday I might write some of this down, and I would like to be able to cite chapter and verse. If you look at the really early versions from the early 90s, it's clear that they're not completely clear about whether matching is helping you with identification relative to estimating a parametric model by least squares. And in fact, there were a lot of folks in the early years during the hoopla period who thought that, matching is somehow different, that it's not somehow, well, it's not exogeneity, it's conditional independence, but really, even with the parametric model, we were only ever really invoking conditional independence. That goes away. Deheja understands this. The published version is very clear about it. But the field did not always understand it. Now, during this period, I was getting a lot of matching papers to referee. Not surprisingly, this is how I got to know Michael Lechner, for example. I got his papers to referee. And a lot of them, I'm sympathetic because I think a lot of people were writing a matching paper because they wanted to learn how to use matching, which is a reasonable way to learn a new technique. Write a paper using it, right? And at the same time, there wasn't a lot of thought about the external validity of the existing work. So the Deheja and Waba paper would be hard to underestimate its influence, right? So if any of you end up taking the short course I'm giving, we'll talk about this in detail, but basically they took this old data set where sort of standard estimators performed very poorly. They did matching on it and got wonderful estimates, really low bias. And they said, Hosanna, we have found the way. And the field said, Hosanna, they have found the way. And so I get this paper, I might be making this up, it's for the Review of Economic Studies, so a very good journal. It was a paper about residential, like land use in the city of Chicago in the 1930s. Remember that the Durbin-Wu-Hausman paper is about a job training program in the US in the 1970s. So in this paper about land use in Chicago in the 1930s, the authors say, well, Durbin and Hausman have shown that matching solves the selection problem. Full stop, right? It's a marvel. What can it not do? And there were a lot of papers like that. It was like people put this external validity interpretation on the Durbin-Wu-Hausman paper, like, oh, they did this one little thing here in the context of this very unique training program, and therefore matching solves the selection problem. And we don't have to think anymore. It was very reminiscent. I'm old enough to have sat in seminars at Chicago where somebody in the audience would say, how did you deal with the selection problem? And the speaker would say, I did the Heckman two-step, right? With no exclusion restriction. And everybody would nod and say, all taken care of. That's great. And on we would go. It was very like that. It was like, oh, I did matching. Oh, well, problem solved. No more thinking required. That confusion about what matching could do and could not do, which would partly, as I have in the last bullet here, was sort of a confusion of the difference between estimators and identification strategies. Right? Matching is an estimator that builds on conditional independence, just like OLS estimation of the parametric linear model is an estimator that builds on conditional independence, but adds in a parametric functional form assumption. It took the field a long time to sort that out. That was another lesson I took away as I was reflecting on these things over the past few days, is we're slow as a field to learn things. It takes a while. Maybe that's good. Maybe we don't rush around and follow fads as much. All right, where do I, oop. Oh, now I'm going back. Okay, there we go. 3 views of matching. Is there a clock somewhere, by the way? All right, I used to teach in a classroom at Michigan where they had hidden the clock behind a giant pipe, so you couldn't see it from the place where you were teaching. So I have my own clock. All right. There's 3 ways to think about matching, or I came to the idea that there's 3 ways to think about matching. So what the statistics folks, right, and matching has a long history in statistics before Durbin-Wu-Hausman imported into applied economics. It has a long history associated with Von Ruin and Paul Rosenbaum and blah, blah, blah. And there's this whole mystery that I didn't put a slide on about how they never worried about getting consistent standard errors until Abadi and Angrist and those people came along, or Abadi and Imbens came along. 30 years, right, of doing stuff quite happily without consistent standard errors. It's all good. That sees it as sort of a version of case control studies in medicine, right, where you have a bunch of people who have some condition and you want to compare them, you're going to do something to them, and you want a comparison group, and so you select out of the hospital records a bunch of other people who kind of look like them. That's a case control study. You start with the cases, you go find the controls, off you go. That's how a lot of people in stats still kind of think about matching. There's a second tradition that centers on Gary King, who is a professor in the Department of Government at Harvard. And he wrote this paper called Matching as a Non-Parametric Preprocessor, which appeared in Political Methodology, maybe APSR, I don't remember. But it was a big deal, very influential paper in political science. I was actually a referee of the thing at the first journal it went to. And I did not recommend rejection. I just want to be clear. I did offer many comments. But there, they sort of frame matching as a preprocessor, right? You're going to do something else. You're going to do some parametric thing. But why not just do the parametric thing on units that kind of look alike, right? So you can think about it as sort of a tool for, in a loose sense, imposing some kind of common support, or at least reweighting so that the untreated units are not so divergent from the treated units. That's all fine and reasonable, but it's a very different way of thinking about it than I think most economists have come to think about it, or at least most of my friends, let's say, have come to think about it, which is as an application of non-parametric regression. Economists really like regression. We really like conditional mean functions. And so you can think about what matching is doing as estimating a conditional mean function, as doing a non-parametric regression of the untreated outcome, y0, on either x or the estimated propensity score, p hat of x, using the untreated units. That gives you a conditional mean function, an estimate, a non-parametric estimate. Now, you may have a parametric propensity score model, so the entire thing may be semi-parametric. But this final stage is a non-parametric regression, so you're not imposing functional form on this thing. And then you use the predicted values from the non-parametric regression as the estimated expected counterfactual to associate with each of the treated units. I like that, but these are different views. It would be really interesting in one's spare time, when one is not writing handbook chapters that go on forever, to kind of write like a big picture piece that said, here's different ways to think about this thing that different disciplines do and think about differently. I think we do too little of that. Certainly, I would not recommend that anyone do it before tenure. But if you're after tenure, you can do some of that. Statistical software. So this is interesting too, right? The role of statistical software and the choices that people who run the major statistical software packages make in the way that we do empirical work. So once upon a time, in the early days of matching, there was no kind of official matching software. There was some sort of very limited nearest neighbor matching thing built into SAS, I believe. But Stata, for a long time, had nothing. And they held off for a long time, interestingly, which they did not do when they recently introduced machine learning stuff. They held off for a long time to sort of let the field develop and I think get a sense of what people liked and what people didn't like. So in the beginning, there was all this kind of user-written software that circulated. There was a program called Match. There was a program by Sasha Becker. I don't remember what it was called. And then there was this program that I think achieved the greatest popularity, at least among US labor economists, which was PS Match 2. And PS Match 2 was written by Barbara Cianese and Edwin Leuven when they were a couple. And I think the demise of the couple is partly responsible for the demise of the program, but that's merely conjecture. I don't know. But it was a program, and it would let you do kernel matching. And of course, I have a horse in this race, right? Because we talk about and kind of develop kernel matching in the papers with Heckman. And so I particularly like PS Match 2 for that reason. Now, kernel matching, as you may or may not know, requires a bandwidth choice. You have to decide, right? You're doing this non-parametric regression that I had up there before. The non-parametric regressions always have tuning parameters. That's part of the joy of non-parametric regression. And the tuning parameter trades off between using more distant observations and getting a more precise point estimate of the conditional mean function. It turns out that in applied work, the most common bandwidth for people who used PS Match 2 to do kernel matching was 0.6. Why was that? Because that was the default. And so if you didn't, this is probably not a fortunate aspect of the program, it didn't force you to pick a bandwidth. If you did nothing, it would just pick 0.6 and give you a number. And you'd say, oh, that's great. And Barbara and Edwin are pretty smart, so probably they know what the bandwidth should be in my application. So off we go. Stata, as I mentioned, I will defer the story about how PS Match learned to handle ties until the reception, if anybody wants to hear it, but it involves me. Stata held off for a long time. My sense is that this sort of decision was made by some combination of David Drucker, who was like the head person at the time at Stata for these things, and my colleague, former colleague Matthias Cataneo. And they chose. He chose, one of them chose, both of them chose to exclude kernel matching, which is fine. But that I think was the demise of it in a sense. Right? They chose nearest neighbor matching, they chose inverse propensity weighting, they chose double robust, which I'll say a little bit about later on. And that, you know, when you change the relative prices of things, who would have thought as economists, when you change the relative prices of using different methods, right? I could use kernel matching in the kind of, you know, samizdat user-written software PS Match 2, or I can use something else in the official fancy Stata TFX command. You know what's going to happen, right? And so that's giving a lot of power to Stata. Yeah, maybe that's fine, maybe that's not. I'm a big Stata. They send me Christmas cards. It's no, I'm just kidding. You laugh. They do. They send me Christmas cards. Oop. Now see, I want to hit the same button the other direction, and that doesn't work. It just goes further. All right, I want to talk about the horse race papers a little bit. So Marcus Froelich, he's now a full professor at Mannheim. This is one of the things that happened when you've been doing this for a while, right? So I knew Marcus when he was, wet behind the ears and kind of nervous and gangly graduate student with Lechner. And he wrote this paper pretty early on in his career. It was the first sort of important horse race paper that compared different matching and weighting estimators. And one of the main things that you take away from this paper of his is that inverse propensity weighting doesn't do very well in Monte Carlo analyses, right? So I'm relying a little bit here that most of you have some sense of what matching is. I would say that the three most common things out there are this sort of nearest neighbor matching, which is like the case control. You pick the nearest comparison unit on some distance metric. The kernel matching gives you this non-parametric regression, but you can also frame the nearest neighbor as estimating a non-parametric regression because there is a nearest neighbor smoother for non-parametric regression. The inverse propensity weighting is a kind of bit of a different business that goes back to Horvitz and Thompson, 1952 in JASA, as a way to control for non-random, non-responsive surveys. So it's basically weighting, it's also based on the propensity score, but it's directly doing weights. It's weighting treated units by their probability of being in the data and untreated units by their probability of being in the data. And there's different sets of weights if you want the treatment on the treated or the average treatment effect. My colleagues at Michigan, in particular John DiNardo, was very into inverse propensity weighting because he had this paper, DiNardo, Fortin, and Lemieux, which was not about treatment effects estimation. It was about decomposing earnings differences. But it essentially does inverse propensity weighting. They use inverse propensity weighting to decompose earnings differences between groups, not really recognizing in their paper, which is in Econometrica, that there's also these applications to treatment effects. And so there'd be these seminars at Michigan where somebody would put up something doing inverse propensity weighting, and I'd say, why are you doing that? It does so poorly in Marcus Froelich's Monte Carlo. Shouldn't you be doing something else? And DiNardo or McCrary, who was also there at the time as a junior faculty member, Busso was a PhD student who was also around, actually my student. They would kind of grumble and stuff. And my sense is that I complained enough times and irritated them enough that they finally said, OK, we're going to do our own Monte Carlo analysis and show that inverse propensity weighting is better. And that they did. And it turned out that it's really important in inverse propensity weighting that you force the weights to sum to 1 in the sample. Now that sounds very trivial, right? They sum to 1 in the population. But it's really important for the performance of the estimator that you force them to sum to 1 in the sample. And that's, in one sense, the main takeaway of Busso, DiNardo, and McCrary. Now they went through heck at the journals to get that published. It's a very nice paper. But their paper ended up kind of rehabilitating, at least in economics, inverse propensity weighting and correcting what Marcus had done. That's the way science is supposed to work, right? Marcus wrote a very nice paper. There's some things he didn't think about. They come along, do it better. We change the way we do our work. It's all very nice. I wanted to also advertise, as part of this trinity of papers, the Huber, Lechner, and Wunsch paper, but I'm not going to say more about it. All right, how am I? Yeah, OK. More recently, there's been two things. And so there's this coarsened exact matching. Some of you may have heard of coarsened exact matching. So the idea there, it's associated with this fellow, Gary King, who I mentioned before, I think, who's associated in the political science department at Harvard. He's a really smart guy and very creative and very kind of very big wheel in the methods part of political science. And his idea was that exact matching is really nice. Right? If we think that we can satisfy conditional independence with 5 binary variables, then in a data set of reasonable size, we can just match people exactly on the 5 variables. Right? We can compare treated units with some set of values on the 5 variables to untreated units with exactly that same set of 5 values. And that's very satisfying and simple and easy to explain. Now, it becomes less simple if some of the variables that you have that you think you need to satisfy conditional independence are continuous. because then you're not going to, they're literally continuous, and of course, economists use continuous in a very loose sense relative to the formal mathematical definition. We'll talk about years of schooling as being continuous, for example, which is not. Then if the variable is continuous, you aren't going to get exact matches, and you have to start to worry about these things, about how you define the distance metric. What's close enough? How close should I be to matter? And so his idea is just to say, well, let's take the continuous variables that we want to match on, and we'll discretize them. And then we can do exact matching on the discretized variables. He's actually, there's, and he wrote statistical, he's very clever about this. He does what you need to do. He writes data code, he writes R code. It's easy to use, it's well documented, blah, blah, blah. So CEM has had some success. My concern about CEM is twofold. First of all, it provides a lot of discretion to the researcher because the researcher gets to pick all the breaks that are used to discretize the continuous variables. When I have discussed this with him, he'll say, well, but most continuous variables have natural breaks. Right? In the US context, you know where to break the schooling variable. There's traditional ways to do that. But if you're conditioning on lagged income, and you want to discretize that, where are the natural breaks? I don't think there are natural breaks. And so the researcher could, in theory, misbehave. We worry a lot about researcher misbehavior now, p-hacking and all that kind of stuff. The researcher could pick the breaks consistent with the results they want. My other concern is that, in fact, it's a bit mislabeled, right? You're not actually doing exact matching if you coarsen to get there. There's still differences in the x within the bins, right? And we're sort of making those go away. And then we say the word exact, and we're all happy. So I'm not as enthused about CEM as Gary King is. There was actually a paper at the EFO conference I was at last week that was using it. I was stunned. I didn't tease them too much. The other estimator I wanted to remark on is the so-called double robust estimator. So this comes to us from epidemiology. And this whole thing is fascinating because there's sort of 3 or 4 competing matching and weighting literatures in different disciplines that mostly don't talk to each other. Right? There's one in stats, there's one in econ, there's one in epi, there's sort of one in political science. And there's a few people, like Imbens reads the stat literature because he hangs out with Rubin. But most people don't read outside their literature. And so you get these parallel developments that are dissimilar. Anyway, double robust comes to us from epi. And the idea is that you combine a parametric linear model with inverse propensity weighting. So you weight the parametric linear model when you estimate it with the inverse propensity weights. And you can show, and this is where the name comes from, that if either the parametric linear model or the weights are exactly right, right? So that you have written them down to capture exactly the population relationship. You only need one. That's why it's called doubly robust, because you can get one wrong. But as long as you get one right, your estimator is consistent. Now, my response to that, I actually shared this with Wooldridge during the pandemic. We were at an online conference. And I said, well, here's my diss of the double robust estimator, which is 0 plus 0 equals 0. So this is the probability that you get the propensity score model exactly right, and thus the weights. This is the probability that you get your parametric linear model exactly right, and they add up to that. So I've never been quite sure why people get all excited about the double robust property, because it seems to me like saying, well, you know, if you find a needle in that haystack or a needle in that haystack, then you're golden. You have a needle. It's like, well, okay. All right. See, this is very much, I promised you, this is like big picture, history of thought, ranting. So I would say that there's still too much attention in this literature to estimation methods relative to the time that we devote to making substantive cases for conditional independence. Now, it's very hard to sell a conditional independence paper in the US. It is less hard in Europe. There's a vast genre of program evaluation papers in Europe that rely on conditional independence. In part, that's because register data makes it a lot easier to sell conditional independence relative to the kind of survey data that we usually have in the US. But even a lot of those papers don't really make a case. They just say, oh, well, we've got the integrated employment biographies from the EAB, so we're done. We don't have to think about whether we have conditional independence or not. That's not really right. This is the last slide on matching. So we're going to get to talk about model selection a little bit, which I like too. I think there's still reasons. I'm sometimes asked to defend matching now as if it were all a bad dream or something. I don't think it was all a bad dream. I think there's still reasons to like matching and weighting estimators relative to the kind of pre-existing practice of just writing down a parametric linear model and only entering the x's as main effects. We still do an awful lot of that. This is maybe part of the transition into model selection. You have a lot more control over how you're weighting the observations, right? This is something that we're coming to now in difference and differences, right? Bacon and Shea Martin and all these other people are figuring out, oh, we might want to have some control in difference and differences over how we weight the individual comparisons that underlie the aggregate difference and differences estimator, right? That's what those folks are doing. That seems to me wonderful. There's an analog here to matching, right? Matching is helping us control which untreated units play the biggest role in thinking about the counterfactual for the treated units. And the positive thing that you can take away from Durbin-Wu-Hausman is that in environments where the treated units are very different than most of the untreated units, matching can get you a lot closer to the truth than a parametric linear model with the x's entered as main effects. Because in that model, the untreated units that don't look like the treated units are going to drive the coefficients because there's so many of them. That's what happens in the Durbin-Wu-Hausman context. Matching presses you to look at the support condition, which the parametric linear model does not press you to do, and really IPW doesn't press you to do. Should we mourn the demise of kernel matching? I should, probably, because my citation count suffers from that. I'm not sure that you should. I teach it a little bit in my course. And you can decide about double robust. All right, model selection. So I have 12 minutes, according to my clock, to select models or to convince you to think differently about selecting models. So when I was little, when I was taking like undergraduate econometrics from Patluri Rao, and at the University of Washington in Seattle, his shtick was that he wanted to train us to be $50 an hour economists and not $5 an hour economists. We got to hear that in class almost every day. $50 an hour, not $5 an hour. This was a long time ago. So it was all about estimating the linear model by OLS. It was all about using t-tests to think about whether individual variables would stay or go. Because oftentimes what you were doing in those days is you had, an outcome, a variable whose coefficient you cared about, and some other variables. And you would ruck around deciding which other variables would go into the final specification that you reported in your paper or whatever. And you would use t-test to do that, or you would use f-test to do that. The usage chow test seems to have gone away, but we used to talk about chow tests. If you had non-nested models with the same dependent variable, right, so you have y on x or y on log x, you would use r squared or r bar squared. R bar squared is kind of sophisticated, right? We penalize you for using more degrees of freedom. In nonlinear models, we would use AIC and BIC, the Akaike information criterion and the Bayesian information criterion. Some of that older stuff, and this is one of these things, like I try to explain the Cold War to my daughter, and I don't know how to make it real to her, and I'm not sure how to make 70s econometrics real to most of the people in this room. It was just a very different thing, more different, I think, than you can really imagine. And I'm trying to give you some flavor of how different it was and how far we have, if not advanced, at least moved. So, oops, there's a typo there. That should be selection. If you did fancy model selection in the 70s, you were doing stepwise regression. Right? So stepwise regression was a formal statistical algorithm for deciding what variables would go on the right-hand side of your model. And you could do stepwise regression down, which meant you started with all the variables and you gradually threw them away. Or you could do stepwise regression up. That means you started with just the thing you cared about and you thought about adding them one at a time. And of course, there were 50 different ways to do each one because it mattered what order you considered these things in because you were using statistical tests along the way to decide what goes in and what goes out. The way I was taught in undergrad and grad school, not that it came up much in grad school, was that this was atheoretical and bad. It was letting the machine do your thinking for you, which at the time, it had like ominous organ music. Oh, you're letting the machine do the thinking for you. That's not what you want to do. So think of that, how different that is than now, right? That's how we were trained back in the day. There was also the Durbin-Wu-Hausman test. Now, in some quarters, this is called the Hausman test. In Heckman land, it is called the Durbin-Wu-Hausman test because Heckman doesn't like Hausman. And so what you would do in the Durbin-Wu-Hausman test, so here you have a parametric linear model, and you have a variable of interest, and you're concerned, but you're not certain that the variable of interest may be endogenous. It may be correlated with the error term. And so you first estimate your equation by least squares, so implicitly treating the variable as exogenous. Then you estimate your equation by IV, implicitly treating it as endogenous. And this, of course, is before we worried about instrument strength or any of those sorts of things. So the set of possible instruments was much larger then. You would test the null of the equality of the two estimates using this formal test. And then if you failed to reject the null, and the null is exogeneity. This is the truly amazing part, right? Is that the null is exogeneity. And so it's to your interest as a researcher, since you want to have small standard errors, to not have to do the IV and report the IV. So you really want the null to be true. Unfortunately, the test doesn't have a lot of power in most cases. So you would if you rejected the null of exogeneity, you would report the IV estimate and its standard error. And if you failed to reject the null of exogeneity, you would report the OLS estimate and its standard error, which of course is usually going to be substantially smaller. There's a nice paper by Guggenberger from 2010, I think, where he shows that if you think about this whole thing as an estimator, and so you report a standard error that actually captures the variation due to the model selection process, that the procedure we used to do in the 70s is completely hopeless in terms of getting the size and all that kind of stuff right. But that's not how they thought about it back in the 70s. They thought, oh, we're going to pick which one of these things we do, and then we're going to report the standard error from that and kind of ignore the model selection stage. This is a bit different to me than just using stepwise regression to choose conditioning variables. To me, this is using a statistical test to choose an identification strategy rather than just to choose a conditioning set. Now, in the intervening years, this test was rendered obsolete by the late revolution in IV, right? So now we know that if we're in a world with heterogeneous coefficients on our potentially endogenous variable, that OLS and IV actually have different population estimands. And so if we reject the null of equality, right, that's that third and fourth step there, it could be because the variable is endogenous, or it could be because there's different population estimands, and we have just noticed that. So nobody does this too much anymore. There's a nice paper by my colleague, my Wisconsin colleague Bruce Hansen, that suggests averaging the OLS and IV coefficients where you pick the weights on the two using the Durbin-Wu-Hausman test statistic, which I thought was kind of clever. There's a lot of kind of model averaging stuff in the air at Wisconsin because people used to actually write Bayesian model averaging papers there until Durloff and Salvador left. There's more about this in my recent, actually hasn't forthcome yet, but it is forthcoming in Labor Economics with Dan Black and Evan Taylor, my student, and the late Bob Lalonde and his student, Juan Ju. We didn't get much explicit specification testing at Chicago. I took classes from Tom Ross and Jim Heckman and Bo Honore and Arnold Zellner. I actually met somebody I dated for a while in Arnold Zellner's class, so it's the romance of Bayesian econometrics, I guess. My own experience with thinking about using formal statistical tests came in the stuff that we did in the JTPA data that I did with Heckman and others. And there we chose propensity score models based on a measure of fit that built on successful prediction. So we were choosing propensity scores based on their ability to predict who participated and not. Now there's an issue with that in that if your set of variables you're considering has an instrument, you will be led astray. And we didn't fully appreciate that at the time. I think I didn't fully appreciate that at the time. But that was my first experience with sort of a formal algorithmic model selection strategy. And I found it really interesting. And in the course of that, Heckman put me on to this book, which I've always remembered because one of the authors is called Zucchini. So it's a Linhart and Zucchini have this model selection book. You can buy it on Amazon for like $30. And it was fascinating to me at the time because it was all this stuff, it was all the statistics stuff that I hadn't seen in econ. It's fascinating to me now because it shows just how much people had thought about algorithmic model selection methods in 1986. Right? And I'm going to come back to this theme as I rush through the last few slides, that things aren't quite as different as they seem now that we are doing machine learning. So then I moved to Canada. My first job was at Western Ontario. And basically, as best I could tell, every econometrician in Canada was trained by Russell Davidson and James McKinnon, usually together. And if you look at their old book, their big, thick, old econometrics book, it's like the encyclopedia of tests. And so people in Canada did a lot more testing than people in the US. And that was a lesson to me about the importance, which I guess I should have known having gone to Chicago, about where you went to school and who trained you, that it mattered for applied econometric practice in an extent to which I hadn't previously understood. All right, here is my argument that there's nothing new under the sun. That's too strong. There is new stuff in machine learning, but I think we way overstate the amount of new stuff in machine learning relative to what went before. So first of all, I have these two examples, which are very self-serving, of papers that used modern machine learning methods 20 years ago. So one is Heckman, Ichimura, Smith, and Todd. Heckman got all excited one time about classification and regression trees. And so we got some CART software on a floppy disk. And I was assigned to and spent several weeks learning CART and generating CART estimates of propensity scores. And there is a little tiny section in our econometric paper in which you can read about our adventures with CART. But that is 24 years ago. Okay? Regression trees. Black and Smith, 2004, used cross-validation. So Dan had gotten the cross-validation bug from Jeff Racine, who was his colleague at Syracuse, transmitted it to me. We used cross-validation to choose models in a propensity score as a sensitivity analysis, and we were stunned that the cross-validation threw out most of the X's, because it turned out that the reduction in bias that you got was not worth the increase in standard errors that you suffered. And that was one of my first introductions to this idea, which probably ought to be on one of these slides, that maybe economists shouldn't be lexicographic, that maybe the statisticians have this right. So economists tend to think, first, consistency or no bias. Then, within that set of estimators, we minimize variance. Whereas statisticians will happily trade off, mean squared error, all that kind of stuff. We'll accept a little bit of bias, a little bit of inconsistency, if you can get a big reduction in variance. Now, the non-parametric literature kind of has to adopt the statistician's view. But most economists are really leery to use any estimator that has any whiff of inconsistency or bias, no matter how much it might buy you on other dimensions, which I think is odd. All right. Argument number 2. Machine learning methods often have very specific antecedents in the earlier literature. Stepwise regression and lasso. They're not the same, right? Lasso is a linear model with an objective function that's designed to set a lot of coefficients to 0. It's very clever. So it's not the same thing, but I think they're spiritual cousins, perhaps. Discriminant analysis, cluster analysis, and regression trees, right? These are all tools for trying to separate units into subgroups based on something. And of course, discriminant analysis was used widely in other fields than economics in the 60s and 70s. Cluster analysis was used in political science a lot. They're spiritual cousins, right? Yes, these things are cool. The lasso, I don't want to diss the lasso. It's very cool. I don't want to diss causal forests. They're very cool. My only point is they're not a radical intellectual break with what went before. They're a real intellectual development on a pre-existing path from before. That would be my argument. And finally, 3, a little bit of Marxism, right? Changes in technology mattered here. It mattered a lot for the arrival of these methods that computing became really, really cheap. Right? If you're going to do tenfold cross-validation on a data set with 100,000 observations, that takes a long time, right? It's the same thing, and this was another thing I could have talked about, but didn't, which is that, panel data and duration models. I watched that happen, right? When I first got to grad school, everybody's excited about duration models. You couldn't do duration models unless you had panel data, right? And we just had gotten panel data with the PSID at that time. All right. I'm going to skip that slide so I can wind up here. Here are the paths I didn't take. I could have talked about heterogeneous treatment effects. I'm going to talk about that in the short course. I could have talked about within study designs. That's in the short course too. I could have talked about non-sampling variation. That's in my keynote, which I didn't want to repeat in case anybody is going to come to more than one of these things. I could have talked about fit in structural models, because this really bugs me at Madison. I could have talked about hierarchies of evidence, which are a big deal in some worlds other than economics. I could have talked about where did all the duration models go. Now, I know we are in Denmark, so this is like one of the last readouts of duration models. But they were all over. When I was in grad school, people were really excited about duration models and Kalb, Fleisch, and Prentice and all that stuff, right? Gone. Gone. Nobody in the US does duration models anymore. And most people have no idea even what they are, because they're not taught anymore. Why don't we do GLS anymore? Right? I actually still teach this in my undergraduate econometrics class, because it's still in Woolridge, right? So if you have heteroscedasticity, you could take advantage of it to reweight, right? Put more weight on the observations whose x's say that they have a lower residual variance. That's more efficient. But we don't do that. We just type comma robust, because it's easy. How much are we losing by that? Are there papers that would have had t's greater than 2 if they had done GLS instead of comma robust? Should we care about that? That's another issue. And then another thing that fascinates me, so these are all things for us to discuss during the reception, I guess. And I'm like at the anti-penultimate slide, and the other two are short. And I really love that word, anti-penultimate, which is the one before the last one, right? The one before the last one. One thing that's really interesting about RD, and I think we're heading this way now in Difference and Differences, is that because it's kind of a late developing empirical literature that's developed in this information-rich environment of econ Twitter and everything, that it's become very formalized what specification tests you have to do in RD papers, right? There's just a set of boom, boom, boom. You got to march through and do these things, and if you don't do them, the referee is going to be on you and going to be surprised that you didn't know what to do. And that's just not how it is in, up until recently, the differences papers. It's not how it is in standard IV papers. It's not how it is in matching papers. And I find that kind of sociology of science phenomenon of developing a set of very clear directions for empirical researchers. There's a relationship here also to things like the Campbell collaboration and the What-Works Clearinghouse and stuff that define what good evidence is. We could talk about that too. All right, so much intellectual history, lots of variation in practice. I'm a little bit of a Marxist. And gee, should we be worried about those software companies, that big tech telling us what to do? I don't know. Finally, thanks for everything. I have had so many wonderful associations with Aarhus, and I'm delighted to be here.
If there's one or two who could have a question for Jeff, I think we could do that on the way out.
There's lots of outrageous stuff in there. Almost certainly not all true. They're stunned by all the outrageousness.
Jeff, I still want to evaluate that training program. So what should I do? What is like your 5 bullet points?
Are you allowed to operate a randomized controlled trial?
Sure.
And if so, is there any hope that the comparison group will not receive almost as much training, the control group, as the treatment group, as happened in the last US experimental evaluation of a training program, rendering it nearly impossible to interpret? No, my answer to that, and that's not meant to be a flip answer, if you could do an RCT and have it be interpretable, then that's a nice thing to do. The most recent US experimental evaluation of an active labor market program was the so-called WIA gold standard experiment, since experiments are the gold standard of research. And it kind of went off the rails a little bit because of the fact that it's sort of the opposite of a lot of European countries. In a lot of European countries, these active labor market programs are very centralized. They're run by the unemployment insurance agency. The only way you would get to one of them is through the unemployment insurance agency. And so you can have very clean comparisons. The US is hyper decentralized, right? So everybody loves to have their own training program because then they can say that they're teaching you to fish instead of giving you a fish. And so if you get randomized into the control group of one program, there's a vast panoply of other programs at your disposal. And then it's very hard to measure, right? Because now you're doing a survey and you're asking people to tell you what kind of training program they got, and they often don't really know what it's called. They don't really know what they received. If they didn't like it, they might not tell you about it, blah, 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 blah. And that's kind of the road that the WIA experiment went down. So there's a sense in which I like, maybe this is, and maybe, for sure this is self-serving, but I kind of like my paper better, right? So the Anderson et al. Paper that is forthcoming in the Journal of Human Regressions does JHR? Oh, that's an old one. I'm glad I'm getting laughs out of that. That's great. No, but we use the matched employer-employee data in the US, which is far from costless, let me tell you, right? So this is a paper that was 20 years in the making. We started it when I was in Maryland, right? So 3 jobs ago. And we do kind of what you would do simply and easily in Europe, but with US data. And we get a very clean comparison because we can compare people who got WIA training, got into WIA and got WIA training with people who got into WIA and didn't get WIA training. And so we can make an institutional argument that probably those people who got into WIA and didn't get WIA training probably didn't get any other training. That's what the institutional setup would suggest. And we only have to use admin data on service receipt because we're only comparing people who enrolled in WIA. Now, it's a somewhat different parameter, somewhat, than what the WIA gold standard experiment is trying to estimate. But in the end, we end up with, I think, much cleaner estimates, much easier, oddly, right, much easier to interpret estimates with our non-experimental conditional dependence. We have wonderful administrative data that's not quite as wonderful as Germany, but it's pretty good. Evaluation. So that would be my second choice, and sometimes it might be my first choice. Would be to do, in that context, especially if you have good admin data, the selection on observed variables strategy. There was another question up here?
Yeah, so this is like the big picture question, right? So at one point you made the joke that you wanted to describe how the field has moved, but not necessarily advanced. Right?
Yeah.
Which could be viewed as more tragic than it could be. Right? Could you briefly elaborate what you mean by that?
Well, I think we have advanced. But I think we sometimes take 2 steps forward and 1 step back. As was probably clear, I don't think CEM is a great development. I mean, it's not terrible, but I don't think it's a great advance on other things. In contrast, I think some of the machine learning tools are real advances in our understanding of how to do things. I just don't think that they are a qualitatively different enterprise than we were engaged in before. I think the whole literature on matching methods went very slowly. But at the end of the day, I think that doing something like inverse propensity weighting, it's certainly superior in all of the horse race papers to single nearest neighbor matching with replacement, right? Because it uses all of the data. It gets to under certain conditions, it gets to the semi-parametric efficiency bound. You do have to be careful if you have p-hats that are close to 0 or 1 because they can mess up make the weighting less sensitive, but there's ways in the literature to deal with that. I think that's an advance, going from matching as the statisticians were doing it in 1970 to IPW as an economist would do it now. That's a real advance. So I didn't mean to be negative. I just meant to say that sometimes we move sideways, sometimes we move a little bit backwards. But I think economics on the whole has moved forward over my lifetime. Certainly applied econometrics as a whole has moved forward over my lifetime. But yeah, you're right. That's about the biggest of big pictures.